So what we're going to do today is we are going to look at a little bit of how you would program some of the Project Euler problems first. And then after that, we're going to just look at a set of homework problems or a math competition from somewhere in the world. I am not quite sure why the swivel system is not swiveling. It says the swivel is disabled and it is impossible to enable it. So the only advantage of this is I can actually move around freely without having the camera following me. So I'm going to enjoy that. I can actually stand over here. What I want to do is I want to show you how to do some of the Project Euler problems. And again, by now, I am assuming you have watched the video on how to use Mathematica and looked at the template, unless there's another programming environment you know. I do not care what you program in. I just care that you have the ability to do these skills. There are some people who, for Project Euler, trying to solve these problems in a minute or less, they want to challenge themselves not just mathematically, but also on the computer science side. I know people who try to use a different language for each problem. Or they try to make their code extremely fast. The first few problems you can actually be very inefficient and you can still solve them. As you go further along, it gets a little bit harder. So what I want to do is talk a little bit about how to do some of the first ones. So hopefully this is readable. So it says here, multiples of 3 and 5. We list all the natural numbers below 10 that are multiples of 3 and 5. We get 3, 5, 6, and 9. We sum them, we get 23. What is the sum of all multiples of 3 or 5 below 1,000? Could you do this by hand? Yeah, would this be horrible to do by hand? Amazingly, no. This is actually one of the few problems that's not so bad to do by hand. You can write a computer program to do this. You can write a computer program to do this inefficiently, and it will still run in a reasonable amount of time. The question is, what's the fastest way to do it? So I want to talk a little bit, and I've got some comments. I'll circulate these eventually. So I'm going to define the problem 1 sum. The name is because this is coming from problem number 1, and it's a sum function. And it says the sum of n is the floor of n times the floor of n plus 1 divided by 2. And the reason is if I sum the first n integers, I get n plus 1 over 2. What if I choose n not to be an integer? Well, if I just use the formula n plus 1 over 2, that will work even if I don't put in an integer. And for this problem, I want to sum all the numbers less than 1,000. Not less than or equal to, which is annoying, but less than. So when I look at multiples of 3, there's 333 multiples of 3. When I look at multiples of 5, since I only go up to 999, you don't have quite an integral number of multiples of 5 less than 1,000. You have an integral plus a little bit more. And so you just want to be careful to make sure your program gives you the right answer. So I just put in a floor function here. And again, there's really no computation here because we've already proved what the sum of the first n integers is. And now the answer is inclusion, exclusion. I sum all the multiples of 3. Well, to sum all the multiples of 3, just pull it out to 3, and now I'm just summing up to n thirds. I add all the multiples of 5. Well, I can pull out the 5 and do up to n fifths. But I've double counted things that are multiples of 3 and 5. So I have to throw away 15 times the multiples. And so when I do this, if I run the program, it will get me 233,168. Here's another way to do it. Sum if n mod 3 equals 0. So this means if n is a multiple of 3, the 2 lines here means or n is a multiple of 5, I'm going to add n to the sum, otherwise I'm going to sum 0. And I just go from n from 1 to 999. Which do you think is better, this method or this method? The first method using the formula, the second method just summing all the things by brute force. Both answers are right. You can justify either answer. What's good about the first method? It's fast, right? It uses great mathematics that we know. What's good about the second method? It's what? It's readable, it's easier to program, it doesn't require us to remember anything from class. Now, of course, in this class that's not a problem. I know you watch the videos time and time again at home. I know you look at all the handouts, the additional comments. I know you go down to the library and find additional books to read. But other professors have that problem of people forgetting what they've said. And so the advantage of the second approach is you don't need to know as much. As n gets larger and larger and larger, this approach is going to become much, much worse to do. All right, the next problem is the even Fibonacci numbers. Each new term in the Fibonacci sequence is generated by adding the previous two terms. By starting with 1 and 2, the first 10 terms will be 1, 2, 3, 5, 8, 13, yada yada. By considering the terms in the Fibonacci sequence whose values do not exceed 4 million, find the sum of the even-valued terms. One way to do this is, well, let's just generate the Fibonacci numbers. Let's march down the line. And every time we get an even Fibonacci number, we add it to the pile. And every time we don't get an even number of Fibonacci, screw it. Okay? Is there a pattern among which numbers, which Fibonaccis are even or odd? What's the pattern? Yes?
There's two odd and then an even.
Two odds and then an even. One way to prove this is induction, right? Without a loss of generality, it's always induction. When we're trying to prove if it's even or odd, when we add two Fibonacci numbers, even plus even is even plus odd is odd plus odd is odd. We only need to look at the Fibonacci numbers modulo 2. And so once we know, the pattern persists, it's going to keep persisting. So you'll actually have problems like this, properties like this, for all recurrence relations. So really it's index 2, index 5, index 8, etc. So we know, in fact, which indices we need to add. So one way to do this is Mathematica, if you really want to cheat, it actually has the Fibonacci function predefined. It starts the Fibonacci numbers as 1, 1. We want it as 1, 2. So we have to shift indices by 1 if we want to use what Mathematica has. All right, not a big deal. And now what we just do is, current is going to be the Fibonacci number, the first even one, the second. And then what we're going to do is, if our number is less than 4 million, we add it to our sum. The sum was initially 0. And then we increase our index by 3. And then take the next Fibonacci number. And this is a really fast way to march down. What's bad about this approach? It's not horribly slow. No, Mathematica has a very fast Fibonacci function. What's bad about this program? Or what might some purists object to? A Project Euler purist would object to something. I'm sorry? Cheating. Yeah, it's cheating. Why is this cheating? Is this like Alex Rodriguez cheating by karate chopping Bronson Arroyo when he runs to first base? No, it's a different type of cheating. Is it cheating like Alex Rodriguez using steroids?
Yes.
Oh, it's at that level. Okay, excellent. Yeah. All right, this is at the level of Alex Rodriguez using steroids. All right, using predefined Mathematica functions like this is at the level of Alex Rodriguez using steroids. It is not allowed. And I assume that whenever you bike or drive somewhere, you actually build your car from scratch at home. Excellent. Right. Wonderful. Wonderful. So, this is a real question you have to decide. Do you reinvent the wheel? This is one of the reasons why you learn how to program in environments or languages that have really good packages. You don't want to reinvent the wheel every single time. And so for me, I have no problem using the Fibonacci function. I know how to define the Fibonacci function if I had to. And in fact, in a few moments, I think I will define the Fibonacci function. I don't know. We'll see. Yes, I will define the Fibonacci function. As an aside, I was an undergraduate in the 1990s, and I was doing my senior thesis in physics on the Riemann zeta function and nuclear physics. And I needed to generate large lists of prime numbers. And I used the computers in microfilm at Sterling Memorial Library. My boss allowed me to have the computers calculating primes over the weekend so long as I showed up by 9 a.m. Monday morning to stop the calculation and give him back his office computer. And back then it took a while to really generate the stuff. And I actually had to worry about how efficiently would I generate. And I almost cry now when I see how many months it took me to get my data set of primes and how many seconds it would take me to get that now, just in terms of how much things have advanced in the time. Depending on where you are, you sometimes have to be clever. And sometimes you don't. And if you can program something really easily and you don't need the speed, go for it. Over here, I'm using Binet's formula for the Fibonacci numbers. So phi I define to be the golden mean, 1 minus phi is the other root. This is going to be the Fibonacci numbers I need. Okay. Wait a minute, this is not a sum of Fibonacci numbers. If it was a sum of Fibonacci numbers, I would be taking, the 1 over root 5, golden mean to the end, minus 1 over root 5, 1 minus golden mean to the end, maybe shifting things a little bit because I'm defining things differently. I'm not doing a sum. Why am I not doing a sum? So we have two geometric series. And when you have geometric series, you can actually use that to evaluate the sums very quickly. So again, depending on how much you want to use, I have Binet's formula. I need to sum terms in Binet's formula, not a problem. Okay. Any questions about these approaches? So again, I will make this available. I want you to get some sense. So the next one is the largest prime factor. The prime factors of 13,195 are 5, 7, 13, 29. What's the largest prime number? Well, Mathematica is a beautiful command called factor integer. And when you use factor integer, it's not that hard. Okay? So again, I feel this is a little bit of a cheat. So then you want to try to figure out, well, what can I say about things? Well, here is my number. And again, is it cheating to have a list of primes? Mathematica has a command that gives you the nth prime. What you really want to do is at one point in your life, if you're doing Project Euler as a purist, you just generate one really big table of primes that you can then use whenever you need it. Rather than doing that, I will just assume I have already done that, and I will just use Mathematica's prime command. And now when I start to try to figure out what's the largest prime factor, I take my number current, and I see if my prime divides it. And if it does, then I now say my largest prime divisor is that prime. And if not, I don't change it. I then increase my index by 1, and I look at the next prime, and I keep doing this. And I keep doing this while current is greater than 1. This code might actually have, this code actually has a problem in it, and it's deliberately so. It works in this case, but there is a problem with this. So anybody see what I'm doing wrong here? I take my number, I divide, oh actually no, I'm sorry, I have programmed it correctly, I think. Have I? No, I have not. No, okay, I did program it incorrectly, good. Good. So what is the mistake I'm making? I take my number, I see if my prime divides it. If it does, then it's got to be larger than all the primes I've looked at so far. That's my new largest, and I advance to the next prime. And I keep doing this as long as my current number is greater than 1. What's the problem here? Who are my CS majors? Any CS majors here? All right, what's the problem? Yes?
Is it that there's no upper limit?
It's possible that this program might never end. And so instead of taking the number current, let's take another number. Current equals 64 times 3. Let's see if that works. Oh, it worked and it did terminate. So what I was wondering is if this is going to cause problems if the number is divisible by the square of a prime or cube of a prime. Yes?
Well, the very first thing that you can do to reduce the duration for it it's going to run is to have it cap at the square root.
You can have it cap, exactly. So if I put in while current is less than 1, I could add and current is less than or equal to the square root. Oh, but now here I would want my start value.
Yeah, well, you just put the square root in the start value.
Right. So what I can then do is I can add something over here saying start is my current value. And now if I do something like that, now it's going to always terminate. I'm actually a little surprised that it terminated when I did 64 times 3. Because when I'm just looking at it,
Well, aren't you updating current? Your current equals current divided by P.
oh, I'm updating current. Oh, I'm updating current, not my start value. Okay, so I am fine. But, well, let's see. If I start off with 64, the first prime is 2. So now I say, does 2 divide 64 times 3? Yes. So I now replace current with current over here. And now over here, I've increased, oh no, I'm sorry. Oh, I didn't misprogram it, damn it. I programmed it correctly. Shoot. Oh, well. I have an if over here with a comma, and then I have this. I'm not always updating n. I'm only updating n if my number is not divisible by the prime. So I actually did program it correctly. Oh, I had meant to program it incorrectly. I apologize. Force of habit. I wanted to do this to just show how easy it is to accidentally make a mistake and have things just go on and on forever. You want to try to put in little checks, little constraints. And so over here, the danger is, what if my number was, say, divisible by a square or a cube of a prime? Well, here, I'm actually now spending too much time. Once I know that 2 divides it, do I care how many times 2 divides it? No. So should I just say, screw it, let me just move on to the next prime? Or should I pull out all the powers of 2? Which do you think is better? We don't care about those other powers of 2 that divide it. So is it worth spending the time pulling those out? So I have 1 vote for no because we don't need it. But there is a reason why this might be worth doing.
Don't you divide by increasing a smaller number so it's easier to check?
Well, it's then making us divide, doing our modulo checks for smaller numbers. So it might be worthwhile to do a little bit more work here so that all the later calculations are smaller. So I actually think it's probably a good trade-off. Okay. I'll stop there. I think that's enough to look at. All right. Okay. So what I want to do now is I want to go and talk about just solving some general problems. So this is a chance to look at problems live. I have not looked at these ahead of time. So the question is, when you look at these, which problems do you find particularly interesting? Which problems do you find particularly boring? So some of them look fun to me. Number 5, if you know complex analysis, is really easy, but you're not supposed to know complex analysis. So it's like, oh, how do I do this without complex analysis? So some of them are like that. Anyone look particularly interesting? Number 4. Okay. Do you think 17 is special? What do you think? Is 17 special? 17 does have some nice properties. It's prime, but it's more than just prime. What kind? Anybody know what kind of prime 17 is? I'm sorry? Yeah, it is power 2 plus 1. What's the name of these primes? It's a Fermat prime. So the question is, for what values of n is 2 to 2 to the n plus 1 prime? What's the simplest value of n to check? 0. And when I take n equals 0, what do we get? When n is 0, we get 2 to the 0 is 1, so we get 3. When n equals 1, what do we get? 5. When n is 2, what do we get? 17. When n is 3, what do we get? 2 to the 8.
65. It's not a prime. No, that's patently false.
All right, so when we take 3, we get 8. 2, 4, 8, 16, 32, 64, 128, 129. Is it 129?
No, I think it's actually one more. Yeah.
257? Okay. Right, because 2 to the 10 is 1024, so this is 257, prime or not prime?
It better be prime. It's on this list, right?
It's prime. I'll leave it as an exercise. That's also prime. Now these numbers are getting large fast. Okay? Prime, 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 prime. Yes?
With modular arithmetic, it should, like, you can deal with it how fast it's getting as soon as you find a value that's manageable modulo 10.
Oh, for this? Oh,
For the 17.
yeah, but I'm saying right now I'm doing a digression, I'm pontificating. What comes after 4? Prime or not prime? Prime. Actually, no. Composite. This one is prime. It turns out these are related to which regular n-gons can be constructed with just a straight edge and compass. So if you happen to be in the mood of constructing regular n-gons with just a straight edge and compass, this is extremely useful. This is one of the things that made Gauss decide he wanted to become a mathematician. It is conjectured that there are no more primes among this list, that this sequence is just going too fast and doesn't hit the primes anymore. I can give you a heuristic argument that there are at most 3 values of n where this is prime. Right, so the heuristic argument has a few issues, but roughly we don't expect this to be prime that often. If people are interested later in the semester, I'll talk to you about how you can figure out how many primes you should have in a sequence that's going like this. The number 17 is very special. The reason it's so special is one lesson that it is a perfect power of 2 when you're constructing things with straight edge and compass that has a lot of wonderful properties. For this problem, however, determine the last digit, we could have probably done this with 18s or 19s or 12s. The 17 doesn't really matter. But this is just too good of an opportunity to pass up. Whenever you can talk about Gauss, you should do a little bit on Gauss. So we want to study 17 to the 17 to the 17. When you have something like this, what's the first question you have to be careful about? What does this mean? There's 2 ways I could read this, right? I could read it as 17 raised to the 17 to the 17, or I could raise 17 to the 17 and then raise that to the 17. Which do you think this means? I think they mean it like this. And if you look at the size of the numbers, I think this is what they're trying to get at based on how they format things. So they want us to find the ones digit of this. Okay, yes?
Wait, why would that matter? Which way, where we put the parentheses, since it's all multiplication?
Well, 17 to the 17 to the 17 is 17 to the 17 squared. It makes a difference. If I put the parentheses like this, it's very different. This is x to the a to the b is x to the a times b. That's not necessarily the same as x to the a to the b. So we've got to be careful how we parse things. So we want to figure out the ones digit. All right? So we can start calculating. 17, 17 squared, 17 cubed, 17 to the 4th. Yeah. Okay. What? Yes.
Well, there's probably a simple recurring pattern among the ones digits.
Excellent. Why?
Because you only have 10 to choose from, and you can see that some of them won't hit it. Like it'll never end in a 0.
It'll never end in a 0. Once you have the same number twice, from that point onward, the pattern just repeats. And the reason is because you multiply by 17, you multiplied by 17 before. So if it's 2 here, and then later it's 2 again, the pattern will just keep repeating. By the pigeonhole principle, we've got to get into a place where we have a repeating pattern. Right? How long is it going to take us to find the repeating pattern? in this case?
Not that.
Okay, why not that long? Worst possible scenario. Let's say it's really bad. How long could it take us? How many multiplications? 10. We know there's no 0, so we know in at most 10 multiplications we're going to have a repeat. We can actually make life a little bit easier. Do we need to look at 17, 17 squared, 17 cubed? What can we do? Just do 7s, right? All right, first digit of 7. First digit of 7 squared. 9. Do I care about the other digit? No. So this isn't that bad. First digit of 7 cubed. 3. Next. 1. Next. 7. Oh, okay, good. So we didn't have to go that far. So it just took 7 to the 4th. When we raise 17 to the 4th power, we get 1. So what I want to do is I want to look at the number 17 to the 17. Because this is the exponent. And I want to write this as some multiple of some number plus a remainder. What do I want my multiple to be? 4. So it's some number of copies of 4 plus a remainder. Right? So all I have to do is figure out what. What is 17 to the 17 mod 4? And then once we have that, then we can figure out exactly where we are over here. Yes?
Well, 17 is 1 mod 4.
17 is 1 mod 4.
17 is 1.
So are they being kind to us? They're being extremely kind, okay? So this is not a question I wrote. So here, 17 is, I was immediately viewing it as 16 plus 1. It's better to view it as 4 times 4 plus 1. So this is 4 times 4 plus 1 raised to the 17th power. So this is going to be blah times 4 plus 1. So the 4 doesn't matter, so this is the same as 17 to 1. So what should the first digit be? So what should the first digit be? I'm sorry? It should be 7. So I actually was curious to see if Mathematica could do this. It calculated 17 to the 17 without any problems, but with 17 to the x, it got an overflow, where x was 17 to the 17. So this actually did break Mathematica, which is nice. So you'd have to play with it a little bit to get Mathematica to the point where it could compute this. It's not so bad. And so we can check and we can see, is 17 to the 4 equal to 1? Yes. And so I can take x, I can divide by 4. And double check, and it's 1. Everything works. We haven't made any algebra mistakes. But we were able to do this, and Mathematica was not. Now, there's ways around this. There's things called the method of repeated squaring and whatnot that you could help Mathematica get this. If you like problems like this, what class might you like to take? This one, yes. Good, excellent answer, this one. Other classes that would work. There's 2 other ones that are natural. Abstract algebra. What else? There's one other class. I know somebody said it. Number theory. Right? Okay. So I think this is a fun problem. There's a lot of good stuff here. This is a lot of the level of abstract algebra you need on a lot of math competitions. They don't want to write problems, or if they do, they resist the temptation to write problems that require you to know a lot of advanced mathematics. They want it to be problems that are very accessible. And so here, the idea is to break things up into smaller steps. And so here, we've got 17 to the 17 to the 17. Step 1 is to parse what they're asking. and then see, are there any things we can understand? Well, instead of understanding 17 raised to the blue, let me just look at powers of 17, try to get a flavor for what's going on from that. Does number 3 look interesting or familiar? The expression on the left, we've seen the expression on the left before. Where have we seen that expression? Not the coin flipping. So we've got the sum of AK, AN minus K. We have seen that this semester. Where did we see that? Except instead of using the letter A, we use the letter C, I think. Convolution, the Catalan numbers. You know, how many ways to get from the lower left to the upper right in a grid where you don't cross the main diagonal? The difference was when we did it with the Catalan numbers, we were basically getting the Catalan numbers convolved with themselves with the Catalan numbers. Here we're basically getting the sequence convolved with itself as its own inverse. So that kind of seems interesting. I've got, you know, a0 plus a1x plus a2x squared plus dot 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 times a0 plus a1x plus a2x squared plus dot dot dot. Maybe it's not going to be entirely the inverse. And I'm telling you, I always get 1 when I convolve. So I think it's always going to be 1 plus x squared plus x cubed. Do we know what that is? So what does that equal? So what would 1 plus x squared equal? 1 over 1 minus x. At least if the absolute value of x is less than 1, and so let's just assume it's less than 1. So this is convolutions. So the way we get the coefficients here is, well, let's say I want to get an x squared. I could take a constant term here and an x squared term. I could take a linear term and a linear term. I could take a quadratic term and the constant term. So the coefficients here are my convolutions. Does anybody know how to solve this problem? So again, I did not prepare for class today. I have 2 other classes I'm preparing for. There's just only so much I can do. It's much easier for me to just pull something randomly from the web. Amazingly though, this ties in beautifully with something we've done. It's tying in with convolutions. It's tying in with generating functions. If I call this function f of x, I'm trying to solve this equation. Can anybody think of a solution to this? What's the solution? So I have f of x times f of x is 1 plus x squared plus dot 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 equals 1 over 1 minus x. Can anybody solve for f of x? So what would f of x equal? Yeah. So f of x is just 1 over the square root of 1 minus x, or 1 minus x to the negative 1/2. And now if you know the binomial theorem in full glory, where you allow yourself not to just have an integer exponent or a positive integer exponent, or you can do Taylor series, and you can now figure out what's going on. Here is the solution. So they want us to find the sequence. The sequence is just the Taylor series expansion of this. All right. I will show you another way to try to do this problem. It's much harder. But I look at the Taylor series expansion. You know, f of x is going to be f of 0 plus f prime of 0 x plus f double prime of 0 x squared over 2 factorial plus f triple prime of 0 over I guess I'm running it this way, x cubed over 3 factorial plus yada, yada, yada. So I just keep taking derivatives of this and evaluating at x equals 0. It's now a calculus problem. We now need to figure out a formula for the nth derivative. Any idea what we could use to find the formula for the nth derivative? Induction, right? There shouldn't be any delay at this point in the semester, right? When in doubt, just say induction. Probably we'll generate a recurrence relation and we'll solve the recurrence through induction. So from this point, I hope you can see how you would get the values. The key fact here is to notice that this was a convolution. And if you notice it's a convolution, it's not so bad. Then you have to make the leap and say, well, I know what this is. I have a simple formula for this answer. It's just 1 over 1 minus x. Question?
Is this how you would sort of get at what the full glory of the binomial expansion theorem is? By using, I don't know, like a Taylor series expansion of a minus b to a fractional power? Or
Yes, and you would play some games so that the numbers here will converge. Now, imagine you didn't see that this was a convolution problem. How could you approach this problem? What should you do? So all you know at this point is that the sum, k goes from 0 to n, of ak a n minus k equals 1. And do they tell you a0 equals 1? And they tell you a0 equals 1. What would you do if you didn't see the convolution? What would you do? So, goodbye convolution. We're going to completely forget about it. It's gone. We don't see it. All we know is we have this relation. What would we try to do at this point? Well, find a recurrence relation. How would we find a recurrence relation? We've got it. Here's the recurrence relation.
Just by varying levels of n and solving for like a sub n.
So we could solve and we get a sub n is 1 minus the sum. K goes from, we've got to be a little bit careful. When k equals 0, we have an an here. When k equals n, we have an an here. So we get 2an is the sum, I think k goes from 1 to n minus 1 of ak an minus k. And now, if we know the previous values, we can figure out an. The question is this a tractable problem? What might you want to do in a situation like this? What should be your first instinct? So if you're going to be a professional problem solver, if we're going to keep the green chicken, you need to have an instinct here. It's not induction.
it'd be nice if the index started at 0.
Right, but I'm saying I have a sequence. I give you this formula for sequence. I'm trying to figure out what the pattern is. What should I do? I'm sorry? Generate some terms, right? Here's n, here's an. When n is 0, it's 1. When n is 1, we get 2a1 is 1 minus the sum of somebody said, did we make a mistake here? And when k equals 0, we get an. When k equals 1, okay. Right. So over here we have a sum. K goes from 1 to when n equals 1 to 0. There's no terms. It's an empty sum. So what does a1 have to equal? 1/2. It has to equal 1/2. It can be a little confusing. I have a sum. K goes from 1 to 0. Can k go from 1 to 0 increasing? It's an empty sum. It's a problem of trying to write this down when the value n is a little bit small. Once n is huge, like 2 or 3, everything's okay. When I take n equals 2, if I expanded this out, I would get a0, a2 plus a1, a1 plus a2, a0 equals 1. I know this is a half, I know this is a half, so this is a fourth. I know these are 1, so I get 2a2 plus a fourth equals 1. a2 is 3/4 over 2 is 3/8. And you can keep marching down like this.
Are we going from k equals 1 to 1 for the case of n equals 2?
For the case of n equals 2, yes. And we would be able to use this formula when n equals 2. When n equals 1, the formula is a little confusing. When n equals 1, we have k going from 1 to 0. And we'll define a sum going from 1 to 0 to be vacuous and empty. Yes?
How did you get the top equal?
This? Well, when I look over here, I want to solve for an in terms of the previous terms. Where does an occur in this? Well, when k equals 0, I get a0 times an, and a0 is 1. So the k equals 0 piece gives me a 1 times an. When k equals n, I get an times a0, which is another an piece. So when k is equal to 0 and n, I get 2an. Then I have the sum over the remaining ones. The remaining ones are all the values of k between 1 and n minus 1, assuming they exist. If n happens to equal 1, there is no value of k between 1 and minus 1. But once n is larger, then I can write this down easily. And so now I have the value of a2. What value should I calculate next? We've got a0, we've got a1, we've got a2. What should we do? We've got a student here, at least one who's trying to decide, maybe two who are trying to decide, should they come to Williams? What should we do next? Try 3. All right. Let's see what happens when we try 3. 3, it's a little bit more painful. But using this formula, we'll get 2 times a3 is 1 minus, now we'll have a1 times a2, right? And a1 times a2 is 3/16. Then we'll have a2 times a1, which is also 3/16. So hopefully I haven't made any mistakes. And then since n equals 3, we only go up to 2, so we only have 2 things to try. 1 minus 6/16 is 10/16, divided by 2 is 5/16. So we get a3 is 5/16 divided by 2 is 5/32. Okay. So assuming we've done the algebra correctly, and I'm actually fairly confident we have, we now have data points at 1, 2, and 3. Do you notice any pattern going from one to the next?
On the bottom.
The bottom 2 to the n? So 2 to the first, good. 2 to the second is 4.
Oh, yeah.
Looks like 2n minus 1 over 2 is 2n minus 1.
So whatever number we have up here, that's the power of 2 down below. And the odd numbers are just increasing.
Should the third one actually be 5/16?
No, because we have a 2 over here that we have to divide by.
Didn't you already divide by that?
Yeah.
Oh, did I? Oh, if I did, then that's going to change things. So let's see.
And because
Okay, so wait. So then that would become 10/16. Okay, it becomes 5/16. Okay. So if that's the case, things are looking a little bit harder now for the pattern. What should we do? Some of the patterns looking clear. I've got a 1, a 3, a 5. One of the reasons I wanted to start off with the Fermat primes is because you have a pattern that stops after some point. What should we do over here before we try to prove something by induction? Try a few more. Right? We're running out of time. I'm not going to do the next few. There is a nice formula for these. And the reason there's a nice formula is, I know the Taylor expansion. I know Newton's binomial theorem. The problem is it's not going to be as clean as that typo was making it look, because we do have some other factors coming into play. But there should be hope now. So if you do not see the generating function approach, there is a way to do the problem. Is it as easy or as hard as the generating approach? I think it's a little harder. You've got to see a way to rewrite things. You've got to then try to find a way to deal with, how do I prove by induction what this formula is to get what that is? The induction does not seem as clear or as easy, but there is an approach. And again, a lot of these problems, the way you solve them is you just start off and just try to do things. Just try solving, try putting in some values and seeing if it works. Once you start generating values, you have some idea of what the pattern is. Most people have a brain freeze, and they don't see how to solve a problem, so they stop. Do not be afraid to waste paper. Don't be afraid to fill up something with lots of scribbles, and then put it aside and try something else. Try lots of different things and see if any of these approaches work. So what I love about this problem is it is related to a lot of very important things. So we have 1 minute left, 1.5 minutes left. It's not worth talking about another problem, I think. At this point, we don't really have enough time. What I will say instead is I'll just say a word about the general binomial theorem. Let's say you want to expand a plus b to the n. Or maybe a plus bx to the n. You want to expand something like this. What you can do is you can pull out an a, and you can write this as a to the n 1 plus b divided by a of x to the n. And if I write it like that, so long as x is sufficiently small, maybe my series will converge. Which values of n will be easier or harder to expand this? Which is a really easy value of n? I'm sorry? Okay, n equals 0, I asked for that. N equals 0. Which values of n have you already learned how to do? N is an integer, a positive integer. If n is a negative integer, it's a little bit harder. If n is a rational, it's a little bit harder. But there are ways to do this. And then what we were stuck with today is, if I know the expansion of 1 minus x, how is that related to the expansion of 1 minus x to the 1/2? How do I find the square root of a series expansion? All right, so there's a lot of good problems here today. For Monday, I'll give you some additional stuff to read. This is a chance for you to give me some feedback as to how the class is structured. If you like something like this, what I will do is I will give you some specific problems to look at over the weekend, and we'll do a few of these in class.